Thank you. So as Kira said, I'm Andres Cristi. This presentation is called The Two-Sided Game of Googol and Sample-Based Profit Inequalities. It's based on joint work with my advisor, Jose Correa, and Boris Epstein and Jose Soto, also from Universidad de Chile. So I will tell you about this super fun game that we call the Two-Sided Game of Googol. I will define the game, and then I'll tell you what are our results regarding this game. And then I will talk briefly about how it connects to sample-based profit inequalities, or also called data-driven profit inequalities, which in turn relate to mechanism design for online allocation of goods. Okay, so what's the two-sided game of Googol? So maybe I first should say what is the regular game of Googol. It's a game that is equivalent to the secretary problem. And in this game, we have n cards. An adversary writes numbers, one number on each card, some non-negative number. Then the cards are put face down on top of a table. And then we, in random order, have to flip the cards, reveal a number, and decide whether we keep this number or continue flipping cards. And the objective is to get a large number, right? So that's the game of Googol. And to have more fun, we can play the two-sided game of Googol, where the adversary, instead of writing a number on each card, writes a number on each side of each card. Okay, so we have in total two n arbitrary numbers, non-negative numbers, that this adversary writes on the cards. And how we play, so I have here the cards that an adversary wrote numbers on them. Say Kira put 2 n numbers on these cards. And without seeing the numbers, we take the cards, we toss them in the air, and they land with a random face looking upwards, right? Each of them independently, and they land in a random order, right? So, right. So we have this, right? So I took a picture. Yeah, excellent. So we get some numbers in some random order, and we start flipping the cards in this random order. So when we flip the card, so that there was an 11 there, I flip it, I reveal, say, a 0, and we have to decide whether we keep the 0 or continue flipping. We cannot take the 11. Now notice this. We have to take the number we just revealed. So 0 looks kind of a low number here. So let's continue. We flip the 1, and we reveal a 5. So 5 is still kind of small number. So we continue, flip the 8, and reveal a 26. Looks decent. So let's accept it. Right? So that's the game. And the objective I will talk about in this presentation is to maximize the expectation of the number we accept. Okay, and why expectation? Because there is notice that there is randomness in the sides that land face up, right? So the numbers are fixed by Kira and beforehand, but the numbers that we can select are the ones that landed originally face down, right? The ones that landed face up cannot be selected, right? And the benchmark is the expectation of the best possible number we could pick, which is the largest hidden value, right? The largest of the numbers that landed face down. And again, this is expectation in terms of the randomness of the side of the cards. All right. So what's Is there other questions about how the setting is?
Can you repeat the experiment?
Okay.
So you're looking at the worst case over the adversary and the expectation over the...
Exactly. So Kira does the work. So is the adversary. So it's the worst case for the numbers.
And you care about the expected value and not the probability of hitting the maximum.
Yeah, one could ask that question, but in this presentation is the expectation. Yeah, it's not the probability. But okay, in the paper we also look at this objective.
But you do know the distribution?
No. The numbers are totally adversarial, so they are arbitrary non-negative numbers. So I don't know the distribution. I only know that there is randomness in the sides and in the order in which I flip cards.
Order is also random.
Yeah.
And side.
Order and side is random. Yeah. All right, let's continue. So one could say if we cannot pick the numbers that landed face up, then how is this different from the game of Googol? Like if I wouldn't see the numbers face up, and it actually matters that I can see these numbers. And our result is that we have an algorithm, a stopping rule, right? That achieves 63.5% of the optimum, of the expected optimum. Right, and is there a question? No? Okay. And what was known before this? Well, not much because we kind of defined this game, but there is a related result. It is not exactly about this, but one can translate it to this. If we take the game and the order is also adversarial and not random, then there is a 1/2 approximation by Rubinstein, Wang, and Weinberg. And this is actually the best possible. You cannot do better than 1/2.
How is it related to like the Kaplan and Oren in Raz in the upcoming soda? They also take like half a sample.
Right. So here, that paper that you're mentioning, there are 2 n numbers,
Yes.
and at random you select half of them, n, and these are revealed, and then you, in random order, you reveal the other n, right? But here you have these cards, right? So the numbers that are in one card cannot be in the same set.
Okay.
The benchmark is also different, right? Because the benchmark varies with respect to the maximum over all the 2n, and here you don't count the ones that are revealed, right?
I think it's over the n that are not revealed. But it's different. It's subtle, but it's different.
Which version is harder?
This version is harder because the other version can be simulated by this one, right? If I randomly shuffle the numbers before,
I see.
I can simulate this other game, right? With the
You add correlation.
yeah, kind of. Yes. But this is decided by Kira, right? not by us. Right? But the adversary.
I see. So this version gives the adversary a little bit more power.
Yeah.
That's the point,
Yes.
right?
Yes. A bit
And
more.
how much does he gain the adversary from the little more power?
We don't know because this is not tied. I mean, none of the results are tied. Not that one, not this one. Okay, but let me say also that this 1/2 approximation is very simple. It's just to accept the first value that is larger than all numbers seen so far. Or alternatively, we look at all numbers that landed face up, we take the maximum and set this as a threshold. So that's the 1/2 approximation. And of course, it's also a 1/2 approximation for the two-sided game of Google. Right, so ALG star, our algorithm, is actually a combination of 3 simple algorithms. One of them is this one. I will call this one algorithm 3, and I will explain later. Right? Yes.
Okay, not your algorithm.
No. So there are more results in that paper, but yeah, that 1/2 approximation is this algorithm. Yeah. But this ALG star up there is a combination of 3 different algorithms, and one of them is this one. And that one will be algorithm 3. I will explain later why. So algorithm 1, we call it open window, is to stop in the first value that is maximum among all currently visible values. And visible values is in the physical way, in the physical meaning, right? So if when I flip a card, I change the set of currently visible values, right? So say this is these are the numbers that are revealed at the beginning. Say first I have to flip the 3, I reveal a 5. So now 5 is in the set of currently visible values and 3 is not. Okay? But 5 is smaller than 20, so this algorithm continues. I reveal a 0 in the next card. This is again not larger than 20, so the algorithm continues. I flip the 20 and this reveals a 15, and now the algorithm accepts, right? Because now 20 is not visible anymore, and 15 is larger than the next largest number, which is 6. So the algorithm accepts.
The 20? Because
Sir?
you did arrive to the 20 and it was the biggest visible.
Yeah, but remember that we cannot accept the numbers that are revealed in the first place, right? We have to flip and then decide. Okay, so the 20 in this realization cannot be accepted. All right? Yes, so this algorithm is also a 1/2 approximation for this game. And it's not better than a 1/2. And the instance where it's not better than 1/2 is very simple. It's just 2 cards. It's just 2 cards. One with a 0 and a 1, and another one with very small values. So the only number we care about is this 1, right? And the optimum is then 1/2, because with priority 1/2, the 1 is a hidden value, and with priority 1/2 is not, so it cannot be picked. And the algorithm is actually 1/4, because in order for this algorithm to pick the 1, we need that 1 is hidden value, but also that is the first card we flip, right? Because if we flip first this card, regardless of which of the 2 is looking up, the 0 is the threshold, right? So we accept with this algorithm. So it cannot be better than 1/2. So we have a slightly more restrictive algorithm in which we accept if the number is maximum among all currently visible values and the other side of its card. Okay? So in this case, the blue dotted line is the set. So when we flipped the 3, reveal a 5. As before, we cannot accept. Then we reveal the 0. We cannot accept. And now when we reveal the 15, 20 is the other side of 15, right? So we cannot accept. And say now we flip the 6. This reveals a 16. And now we do accept. And notice that 20 was larger, but it's not the other side of 16. So it's not anymore in the set. All right? And we have an even more restrictive algorithm, which is the one I mentioned at the beginning. We call it the full window algorithm for reasons I won't explain. But it's to stop at the first value that is larger than everything seen so far. And in this particular realization, it won't accept anything, right? Because 20 is a too large a threshold, right? So I put them in this order because it's from less restrictive to more restrictive. That's the reason. And well, 2 and 3 are also half approximations, and they are no better than half approximations. And the example is even simpler than the previous one. It's just 1 card. Then 2 values are almost the same. So 1 and 1 minus epsilon. And notice that since we cannot accept a number whose other side is larger, we can never accept 1 minus epsilon with algorithm 2 or algorithm 3, right? So opt is 1 because opt is any of the number that is hidden at the very beginning, and algorithm 2 and 3 are only 1/2, right? Because with probability 1/2, 1 is hidden, and with probability 1/2, 1 minus epsilon is hidden. And you might say, okay, this is cheating because with 1 card, you accept anything, right? But we could add as many cards as we wanted with very small values, and these don't change the behavior of the algorithms. Right. Also, notice that the algorithm 1 performs very well in this instance. It's actually optimal, algorithm 1 in this instance, because algorithm 1 will see in the set of currently visible values either 1 minus epsilon or 1 at every point in time. So algorithm 1 won't accept any of the epsilons. And when it reaches this card, it will always accept, right? Regardless of what is the visible side of that card. So algorithm 1 in this instance is optimal. So that motivates us to use the 3 algorithms to balance this behavior, right? Because they perform bad in different situations. So that's basically it. So our ALG star is just to randomize between these 3 algorithms. And to give you a bit of the flavor of, or an idea of how we prove this is just a stochastic dominance argument, which is to make use of this simple fact in the box, that if we prove a bound for the ratio between these 2 probabilities for every x, okay, this is the distribution, or 1 minus the distribution, then simply by integrating, we have the ratio for the expectations, right? So that's what we do. And let me show you the plot of this ratio for the algorithms. So yeah, so here I have y1 to y2n as the numbers that are in the cards in decreasing order. So these are the only numbers we're interested in because this is the support of what the algorithm or the optimum can get. And we can actually compute exactly these distributions. Because of this combinatorial flavor, one can exactly calculate these formulas. Once we have these formulas, and one can plot these functions, and we obtain something like this. And again, here we have this balancing behavior, right? So the more restrictive algorithm is good for picking high values, and the other 2 the other way around. And then when we randomize, we obtain some average performance, which is better in the worst case than all algorithms by themselves. So that's kind of the idea. There is more technicalities to it, of course. There is we need an extra parameter k that deals with the pairing of the numbers. That's where this is different to this other model. And actually, this plot looks different for each different k. So there is more to be analyzed, but that's the basic idea of the result. And right, so these are 3 simple algorithms, and we just optimized over these parameters alpha and beta. So of course there is room for improvement because we don't claim that this is the best possible. But I'd say this is interesting because of what comes next. Data-driven profit inequalities. So probably many of you know about this problem, the profit secretary problem. So the regular profit secretary problem is like this. We have n different distributions, right? we have one realization of each distribution, and they arrive sequentially in a random order. And we have to decide when to stop in order to maximize the expectation of what we accept, right? So that's the profit secretary problem. And these models, this online allocation of goods, right? If we have one good and different persons or agents we want to give the item to, and we want to maximize the welfare of the allocation, this can be modeled as this problem, right? And one could say that knowing the distributions is too much. So we can think of the data-driven version of this problem, where instead of knowing the distributions, we only have access to one sample of each on beforehand, instead of knowing the entire thing. And it turns out that with the two-sided game of Googol, we can simulate the profit secretary problem with samples. This is simply by assigning to a card two independent samples of one distribution, right? So for each distribution, we take two samples, put these two numbers in a card, and so on. So I think it's easy, or kind of easy to see that this distributes exactly as the data-driven version of the profit secretary problem. And this means that we have a 0.635 approximation for the profit secretary with samples, the data-driven version of the profit secretary problem. And this is actually strictly better than the best known so far for the IID version of the problem. And this result is from EC this last year now, EC19, where they proved for the IID profit secretary problem with samples 1 minus 1 over E approximation, which is 0.632. It's slightly worse, but strictly worse. So this is an improvement for the general version, not the IID even. And I think this is also interesting because even for the original profit secretary problem, knowing the distributions, beating the 1 minus 1 over E wasn't a trivial task. So yeah, I think it's interesting to have beaten.
Is it like an approximation to some nicer
There is an exact expression, yes, but it's like, I forgot the exact values, but it's like logarithm of 5 minus logarithm of 4 divided by logarithm of 3 minus log 2. So there is an exact formula, something a bit nicer than 0.635 something, but not too nice. But it is strictly better than 1 minus 1 over E, which is 0.632. Yeah. So regarding this other objective, the maximizing the probability of selecting the maximum of the hidden values, we also have this result that the closed window algorithm, the algorithm 2 I mentioned, achieves a probability of 0.452 of selecting the maximum hidden value. And this, I mean, one can think of this secretary problem with knowledge of the distributions. And in that case, if one knows the distribution, the best known I think is 0.58 probability, right? And so with samples we can do 0.45. And we also have a slightly improved result for what we call the large data set setting, which is related to the IID, but when n is large. And it's a generalization of these algorithms. Yeah, so that's it. Other questions?
So
Yes.
what happens when the two becomes like you have pairs on cards, you can have cubes, you can have instead of so instead of getting one sample from distribution, you can have two
Right.
for how does it sort of approach the limit? I guess in the limit it's the distribution.
Right. So for the if one wanted to analyze the three-sided game of Googol, or k-sided game of Googol, the techniques don't extend. The exact techniques we use don't extend. We tried a bit, but we didn't manage to. But the profit secretary problem with samples, there are more results. So I think there is a way of having O of n samples in total, or constant number of samples for each distribution, and achieve the best known for profit secretary, which is, sorry, for the IID version I'm saying. For the IID version, one can have O of n samples in total and get arbitrarily close to the best, which is 0.745, right? But for the profit secretary problem, actually, with distributions, we don't know the exact ratio, actually, yeah.
Okay, let's give Andres time to pick up his cards and take a 10-minute break. Thanks.